Hello, and welcome to the first video of Chapter 15. Now, we begin Chapter 15 with a departure from vector-valued functions. So let me remind you about the sorts of functions that we have so far. So we know we have scalar-valued functions. These are the ones that we're familiar with from, say, Calc 1. These are the ones we worked with there. Scalar-valued functions. And in Calc 1 we did of one variable. Calc 2, you did some parametric equations, so this is scalar valued functions of one variable. These looked like y equal f of x, right? Just some function of a single variable x, right? The idea was you put in a real number, and you get out a real number. Right, this was from R to R. Now, there's a couple ways you can go from scalar valued functions. In Chapter 14, we looked at vector-valued functions of a single variable. Right? And these looked like R, right? A vector output of a single variable. So the idea here was, you put in a real number, and you get out something in either R2 or R3. And of course, you can do this in general to like Rn. You can really consider vectors with as many components as you want, but we just looked at these sorts of ones. But there's another way you can kind of go off of this. Rather than change the codomain here considering components vectors, you could change the input. And so this is the subject of Chapter 15, which are scalar valued functions of several variables. So two or more variables. And these look like, for just two variables, we'll say z equal, say, f of x, y. So now there's two inputs. And so what we're doing is we're taking something in, say, R2 and outputting something in R. So still scalar valued, the output is a scalar, and the input is a point in R2, or we could do of another several variables. I could do something like, how do I want to say this? Let's say z equal f of, we could do many variables here, x2, x3, up through, say, xn. So you could have a lot of different inputs. And these are actually a lot more applicable to the real world. Most functions that people work with are functions of many variables. It's sort of rare that a function just depends on one variable, although these were the topic of the entire Calc 1 class, right? It was just studying these things. And so in some sense, the whole point of that Calc 1 was to get us to this point where we can study functions that are, well, a little bit more realistic, have a little bit more use in the real world. By the way, you might have a natural question here. What about a vector-valued function of several variables? We're going to have to wait a couple chapters for that. We'll encounter those in Chapter 17. They're sometimes called vector fields, and they are very cool. So that's the idea. We're looking at these things, scalar valued functions of two or more variables. So in this video, I really just want to talk about domain and generally how we can visualize these things and sort of what's the difference between these guys and the functions we know from Calc 1. So the first thing to point out is that the domain is not just an interval or a set of points in the real numbers, but rather a region in R2. Right, here we are in R2, the xy plane. And here is, let's say, just some region R in the xy plane. So I'll shade it in because we're talking about the things that are inside of this region. And the idea is that for every point in that domain, every point where the function is defined, we get a value, a real value out of it. So let's say I pick, I don't know, the origin is in the domain, and so that will get mapped to something over here on the real line. So this is z, this is a copy of the real numbers. And let's say maybe this interval is the range. So our range is still an interval. It's the set of all points that are hit by things in the domain. And so maybe that point, the origin, gets mapped over here. And maybe, I don't know, maybe this point in the domain, maybe this gets mapped to this point in the real numbers. All right, that's the idea. For everything here in the domain, it's assigned some value in the real numbers. And I've sort of laid it out here to suggest something. So here we are in the xy plane, and then I've called this axis my codomain here. I've labeled that z, because the idea is we can visualize these functions by taking the z-axis here, the copy of the real numbers, and standing it up so it's coming in and out right here. And that is going to allow us to visualize a function of two variables. The idea is it's going to look like some surface in R3. So to demonstrate that, I have one of our interactive figures here. So yeah, so here the shaded region in the xy plane, let's say that's the domain of this function f. For every point in that domain, xy, we can find f of xy, so the output of the function. And what we'll do is we'll mark the point xy f of xy. So we're going to put the output of the function directly above the input. That's the idea. So there it is there. And we do this, we can do this for every point in the domain, right? We can scan over the whole domain, do this for every point there. Notice if I go out of the domain, that does not have a value associated with it. We only want to consider points in the domain. See how it's getting small, the z value is getting smaller and smaller there. And so what that gives us, if we do that for every point in the domain, what that gives us is a surface in R3 that lies above the domain. Right, so there's, if I look at just the shadow of this surface, it's the domain, but then notice how it has, right, it has some shape to it. That is a function of two variables, or that's a visualization or the graph of a function of two variables. It looks like a surface in R3. So this is sort of, yeah, just our starting point for these guys. We're going to do a lot with them. We're going to want to take derivatives of them, and before that we're going to want to build up limits and continuity of these functions of several variables. We're going to want to come up with ways to generalize past just functions of two variables, right? So immediately we can generalize, right? If we have, say, a region in R3, some volume in R3, we can assign each point in that volume with a point in the real numbers. And we won't be able to visualize it in the same way, but that would be a function of three variables. Every point in some volume, we assign a real number. Harder to visualize, but with the stuff we talk about in this chapter, we'll be able to sort of visualize functions like that. And we'll at least be able to handle them. So to finish this video, I just want to talk about domains, right? So as we know, domains are they're regions in R2. Right, just like a common question to ask in Calc 1 or pre-calc was, what's, the domain of this function? We had to find an interval where it was defined. In our class here in Calc 3, we're going to be, or multivariate calculus, we're going to be finding a region in R2 for which the function is defined. So we'll start off here with a couple of well-known classes of functions, for example, polynomials. And with polynomials, we now have two variables. We have x and y. And so these look a little bit different. I'll say p of xy. The idea is similar to polynomials in one variable. We're looking for powers of variables and sums of those. And we could have sums and products of polynomials in either x or in y. So something like this, so x to the fourth, let's say plus 4 xy cubed plus 2x squared y squared maybe plus 11. Something like this would be a polynomial in two variables, right? So that's the idea. We allow products of the two variables and then sums of powers of those things. And then a rational function is just a quotient of two polynomials. So for instance, we could have something like x squared minus y squared. There's a polynomial in two variables. I'll call this r of xy for rational, over, let's say, x minus y. So this would be an example of a rational function in two variables, just a polynomial in two variables divided by another polynomial in two variables. Now, let's think about domains of things like this. So polynomials, if you remember back to Calc 1, if we just have one variable, the domain is all real numbers. There's no values of the input that can really mess this up and lead to an answer that we can't make sense of, an undefined quantity. Same is true for two variables. So the domain of a polynomial of two variables will be the set of all points x, y, such that x and y are real numbers. Right, so this is the set of all points in R2. So this is all possible values. For a rational number, for a rational function, we can't have the bottom being 0, the denominator being 0. And so what we need to do is we need to prevent that from happening. So we need x minus y cannot equal 0. Right, if x minus y equals 0, that's not in the domain of this. So we want x minus y to not equal 0. So that tells me that x cannot be equal to y. So the domain of this rational function, this particular one, is the set of all points x, y, let's say in R2 here, x, y in R2, such that x is not equal to y. So this might be, I'm trying to think, have you seen the set builder notation before? If you took discrete, you'll have seen the set builder notation. I'm reading it, as I read it, that's exactly what it is, right? This is the set of all points x and y, such that x and y are in R. You could, I could have here said all x, y in R2, all points x, y in R2, such that x, y are in R. That's fine. Or I could do it like I did down here, set of all points in R2, such that x is not equal to y. So that puts this further restriction on it. This little colon here means such that this is satisfied. Collect all these points for which this is true. And so in general, for a rational function, we just want to make sure the bottom's not equal to 0. So that'll give us an equation we got to solve and tell us what we need to have not happen here in order to be a part of the domain. And so a lot of these same rules in things from like Calc 1 are going to be true here as well. So if I ask you to find and sketch the domain of this function, well, we have to think about, okay, when are square roots defined? We can't take a square root of a negative number because we're just considering real outputs. And so for this one, we need 4 minus x squared minus y squared to be greater than or equal to 0. You might remember doing things like this from Calc 1. Right, we need this to be greater than or equal to 0. The difference here is now we have two variables to play with. So I can solve this now for my two variables. The idea is I want to massage this to the point where I can recognize what region it's describing. So if I add x squared over, add y squared over, I'll get x squared plus y squared less than or equal to 4. So now the trick is, right, so we can say now the domain is the set of all points x, y in R2 such that x squared plus y squared is less than or equal to 4. And this is a perfectly valid way of describing this, but I mean, if you recognize it, that's great, and this totally works, but do you recognize what this is? That's really the next step, because we're going to want to graph these things. We're going to understand where this thing is defined. So what does this set of points represent? Well, it's a circle. Notice the x squared plus y squared. If it were just equal to 4, right, x squared plus y squared equal to 4 would be a circle of radius 2. But this is all points less than or equal to 4. So what we get is a disk of radius 2 centered at the origin. And let's go ahead and sketch that. So domains now look like regions in R2. This one in particular is a disk. So notice that here it's less than or equal to, so I did a solid line on the boundary. That's going to be a convention we want to adopt. I did a solid line because less than or equal to. If this were strictly less than, I would do a dotted line. So we don't want to include the boundary. Here we do. And so we get a disk of radius 2 centered at the origin. All these points are where this function is defined. So our next step is to investigate what does the graph of this function look like. That'll be the topic of the next video. I'll see you there.